Okay, so part 3 of the absorption lecture. So in this lecture, you should be able to extend the application of operating line and mass balance for packed columns, and also to determine the minimum liquid flow rate and the minimum gas flow rate for absorption and stripping processes respectively. Right, so we extend the overall material balance to derive the operating line for a packed tower. So in this case, if you notice, the difference is in the notation of the flow rate and composition. So previously, when you have a tray column, you have stage 1 starting at the top of the column and followed by 2, 3, and so on until stage n. So you have V inlet coming in as Vn plus 1, and the composition is Yn plus 1. So the gas leaving is V1 and Y1, the composition, and the liquid inlet was L0 and X0, and the liquid outlet would be Ln and Xn. This was what we have used in the tray tower, but in the packed tower, the notation is different. In this case, so we have number 1 at the bottom of the tower, and number 2 is at the top of the tower. So, I mean, there's no right or wrong way to put the notation. In this case, because I'm following the textbook, and there's no problem following the textbook for this. It's as long as you know the inlet and outlet, because at the end of the day, the material balance is inlet equals to outlet. So in this case, this was inlet equals to outlet. So it doesn't matter if you put number 1 or number 2 at the top or bottom of the column, as long as you know what are the compositions at the top and the bottom. So we have done the derivation previously using the solid free basis, solid free flow rates of the gas and liquid flow rates. But bear in mind, although the flows of L prime and V prime, because these are the inert flow rate of the gas and liquid, but the total flow rate, actual total flow rate of L and V, i.e. the V1, V2, L1 and L2, they are not constant, right? Only the L prime and V prime are constant. So let's say the overall material balance on a solid A for a packed tower as a whole. So if you take the whole column as a control volume, so you will obtain this material balance. However, if you want to just obtain the material balance or operating line somewhere in the middle of the column, so you have this control volume. This would give you a balance around the dash line. Here is just By, so anywhere, somewhere along the column. It will give you these operating line equations. So the x values here and the y values here are the corresponding y and x values somewhere in the middle of the column instead of at the inlet and outlet of the column. Okay. Okay, sometimes the operating line can also be written in terms of partial pressure, P1 of solute A. Okay, so you just Y1 times P equals to P1. So if you multiply everything with P, you will get, instead of Y1 over 1 minus Y1, you will have P1 over P, total pressure, minus P1, and so on. So let's say if x and y are very dilute, then the term y minus 1 minus x and 1 minus y can be taken as approximately equal to 1. Thus, the equation of the operating line becomes this. So you don't have the L prime x 1 minus x and v prime y 1 over 1 minus y, because all these are very small. So you just approximate it equals to 1. So you just end up with this equation if it is very dilute. So in this case, the slope L prime over V prime and the operating line will be essentially a straight line. So when you plot the equilibrium line and operating line for absorption and stripping process, if you can see the difference between the operating line and equilibrium line location in the absorption process and in the stripping process in this case. So let's have a look at an absorption tower. Okay, so you have a V1 and Y1 and also Y2, and then here you have X2 and Y2. I'm just putting the concentration instead of the flow rates here, because when you plot the operating line, it's the mole fraction, it's the concentration. There's not the flow rate is not involved in the plotting. So in the absorption tower, the bottom part of the tower is the concentrated end, and the top part of the tower is the dilute end. And you just have to locate where the location of this sorry, this one is supposed to be x1. Okay, so the coordinate y1 and x1 would be at the tower bottom, so you have the concentrated end, so this would give you y1 and x1, and then x2 and y2 is at the dilute end, so you have at the here at the point of the operating line. So in absorption, the operating line will always be above the equilibrium line. Okay, but whereas for stripping, so if you just put the stripping process, so your solute is in the liquid phase. So here x2, then this one is x1. So your gas phase contains no solute, or very little concentration of solute, and y2. So in absorption tower bottom, the top of the tower is the concentrated end, higher concentration is solute, and the bottom of the tower is the dilute end. So when you plot the concentration at the operating line, x1 and y1 would be here at the dilute end or the bottom of the tower, and the x2 and y2 will be at the top of the tower, the concentrated end. And for stripping, the operating line will be below the equilibrium line. So it's a matter of where the solute is transferred from which phase to which phase. So for absorption, the solute is transferred from the gas phase to the liquid phase. So your operating line would be above the equilibrium line. However, for stripping, the solute is transferred from the liquid phase to the gas phase. So your operating line would be below the equilibrium line. So let's talk about the limiting and optimum ratio of liquid to vapor flow rates. Okay, previously in distillation column, you know that the ratio of liquid to vapor flow rate is important, because the ratio of liquid to vapor flow rate will be used to calculate the diameter and also to avoid flooding within ETC. It's the same concept that you will use for the absorption column. Okay, so in an absorption process, the inlet gas flow, the Y1 is generally set, because you know what is the concentration of the solute in the gas phase that you want to remove. And also the exit concentration Y2 in the absorption column is also specified, because when you design the column, you also will specify like how many % of the solute you want to remove, and you have to set a target of what would be the solute concentration at the gas outlet, for example, to meet regulatory requirements. Also, the concentration X2 of the entering liquid is also specified, or you can know, because if you use pure solvent, then X2 will be equal to 0. Or if you use a recycled solvent, then you also know what would be the concentration of solute in the solvent that you use. So the amount of the entering liquid flow, L2, or if you use inert flow rate L prime, is open to choice. Okay, you only specify this one, you specify the flow rate, you know this one you should know, and also this one is your target, and then you can also obtain V2. However, the liquid flow rate for absorption, you have to decide. It's open to choice. So what would be the choice of the optimum liquid to vapor flow rate ratio? Will depend on the economic balance. If you have a very high liquid to vapor ratio, you will require a large liquid flow rate and then a large diameter column. But if it's too small, then you have small diameter but high tower, which is also not good. They're also costly. So you will need to know or gauge what is the limiting case in absorption, which is the L min. So compare this with the distillation previously. In distillation, you have the limiting cases is what? R min. Okay, so you know that this would be the minimum reflux ratio. So you will decide the optimum reflux ratio to be 1.2 to 1.5 times the minimum reflux ratio. So same thing with absorption. You need to know what is the limiting case. You need to know what would be the minimum liquid flow rate that you need, such that you can achieve the target from Y2 to Y1 to Y2. Then when you determine L min, then you can take the optimum liquid flow rate to be 1.2 to 1.5 times the minimum liquid flow rate. Okay, now that you know why you need to determine the minimum liquid flow rate for absorption, so how to actually determine the liquid flow rate for absorption. So just imagine or visualize that you have a absorption column here with inlet gas flow rate V1, Y1, in outlet gas flow rate V2, Y2, inlet liquid solvent flow rate L2 and X2, and outlet liquid solvent flow rate L1 and X1. And you can specify the concentration of gas coming in, and you can target what would be the concentration of gas coming out, and you can specify also what's the concentration of solute in the inlet solvent. But the thing that you cannot specify is this one, X1, because X1 is the concentration of solute coming out will depend on the liquid flow rate. So when you want to specify what is the minimum liquid flow rate, you cannot specify two things, right? So your degree of freedom is limited. So let's say if you want to plot the operating line and equilibrium line for an absorption column. So let's say this is your equilibrium line. It's not a straight line, but yeah, it's just a relationship of y and x at equilibrium of the solute. Then you want to plot an operating line. So you know x2 and y2, so you can plot the x2 and y2 on the graph. So here is x2 and here is y2. So you have one point for the operating line on the graph. And then you also know y1 because you specify. I mean, you know what is your feed concentration of the solute, but you don't know what is x1. So for limiting case in absorption, L min, like distillation, is where the operating line touches the equilibrium line. So you have to find out what would be a straight line that will touch the equilibrium line. So you know one coordinate is y1, so you don't know what would be the x1. So then this would be your maximum value of x1 possible, x1 max. So this is then the limiting case for absorption column. So this would be the operating line at L minimum, which will give you the maximum concentration of solute in the outlet liquid phase. Okay, so this is what in the chart above here shows. This is the operating line for minimum liquid flow rate. So also to recap to you, what was the operating line for absorption column is y equal to L over V x plus V1 y1 minus L1 x1 over V. So this is your y equals to mx plus c equation. So when L is minimum, meaning you have the minimum gradient. So what would be the minimum gradient is when touches the equilibrium line here. It cannot go beyond the equilibrium line. So it cannot. So it has to be here. So when you get this, you can use the operating line to determine the L min. We will show you in the example after this. So, but when you have actual liquid flow rate, let's say you specify the actual L would be, let's say 1.5 times L min, then you will have a different value of x1. Your x1 will be less than x1 max. Okay, then you have another point. So this is your actual x1. Then you will have a different, and this is your actual operating line. So that is where this chart shows. So this is your operating line or actual liquid flow rate, and this would be your actual x1 when you have the actual L prime. For stripping, the stripping column, so your solute is in the liquid phase. So you have L2, X2, and then L1, X1 at the outlet. So your stripping gas is V1 and Y1, and also V2, Y2 at the outlet. So in stripping, what you specify is the inlet liquid solid concentration. Outlet you specify, let's say you want to remove 90%, then you can also estimate what would be X1. And then you also know what is Y1 because your stripping gas, either it's pure gas or recycled gas, then you know what would be the solid concentration in your inlet stripping gas. But what you don't know for stripping, when you don't know the V, is you don't know the Y. Y2, the outlet gas concentration. So that's why this, in this case, it said that you need to find out what the V minimum. If for absorption, you will find out L prime minimum, but for stripping, you have to find out V minimum. So let's have a look at the operating line for stripping process. It's the same operating line equation, it's just where it is located is below the equilibrium line for stripping. So L over Y equals to L over V plus V1 Y1 minus L1 X1 over V. So in this case, if your V is a minimum, if your V is the minimum, then your gradient is a maximum, right? Because when your denominator is small, then the value of the whole fraction is big. So when you plot the operating line and equilibrium line for a stripping process, so this is Y, this is X, let's say this is your equilibrium line, then you plot this operating line X1 and Y1 is set. Okay, because in stripping, this is your dilute end. So the bottom of the tower will have the lower concentration. So this will give you the first point of the operating line. And also you can target what you can know what is, you know what is X2. So X2 you know. Just that you don't know Y2. So what would be the maximum value of Y2? Then you will have to find out where will the operating line touch the equilibrium line. So same thing like what we did in absorption. So this would be the maximum value of Y2 if you were to use the minimum value of V, stripping gas. So this would give you Y2 maximum. So then you will have an operating line. This would be what your operating line will look like if you use V minimum. So you have the maximum L over V, maximum gradient. So that is what the chart here shows. This would be your operating line for minimum gas flow. So let's say if you decide to use V, actual V equals to 1.5 times V min, for example, then you will have the actual operating line, and your Y2 will also be less than Y2 max. Let's say this would be your Y2 when you use the actual operating line. So you will have a new point, X2 and actual Y2, then this would give you your actual operating line for the actual gas flow rate. So that is what this chart shows here. This would be your actual operating line for actual gas flow rate. Okay, let's do example. Let's say you have a tray tower absorbing ethyl alcohol from inert gas stream using pure water at the given temperature and pressure. The inlet gas stream flow rate is 100 kmol per hour and contains 2.2 mole% alcohol. It is desired to remove 90% of the alcohol, and the equilibrium relationship is given y equal to 0.68x for this dilute stream. So the question A, what is the minimum liquid flow rate, L prime minimum? And question, should be part B, using graphical method and the Kramzer equation, determine the number of trays needed if 1.5 times the minimum liquid flow rate is used. So as usual, draw a diagram, put all information you know. So D1 equals to 100 kmol per hour, Y1 equals to 0.022. Okay, V2 and then Y2. You don't know yet, but you can calculate. So your inlet flow rate L2 you don't know, but X2 is 0 because it's a pure water. Then your outlet L1 and X1 you don't know. So the pressure given is P equal to 101.3 kilopascal and Y is equal to 0.68x is equilibrium relationship. Sometimes in the book you may see they put Y star just to indicate that this is equilibrium relationship, because we don't want to confuse you with the operating line equation, Y equals to mx plus c. Okay, so first of all we want to find out what would be the L minimum. So write down the operating line equation in terms of solid free basis. V prime, Y prime, wait, Y1, okay, just the equation lah. Okay, Y prime, X1, 1 minus X1. So this would be your operating line equation or overall balance equation. So at L equals to L prime minimum, X1 would be equal to X1 maximum. So you replace this equation with these terms. So V prime, Y1, 1 minus Y1, plus L prime, X2, L prime min, okay, is to V prime, Y2, 1 minus Y2, plus L prime min, X1 max over 1 minus X1 max. Okay, now we want to find out what is V prime. So V prime equals to V1 times 1 minus Y1 equals to 100 times 1 minus 0.022 equal to 97.8 kilomole per hour. And then we can find Y2 from material balance. Okay, so we know that you want to remove 90% of the alcohol. So you know V2Y2 equals to just 10% left from the feed. Okay, in the feed there would be 0.022 times 100 kilomole per hour. So V2Y2 would be 0.22 kilomole per hour of ethyl alcohol. Okay, and then you can find out also what is V2. So V2 is the total flow rate of the gas, inert gas, plus remaining solute. So V2 would be equal to V prime plus V2 Y2. So equal to 97.8 plus 0.22 give you 98.02 kilomole per hour. That is V2. So if you know V2, you know V2 Y2, you can find Y2. So V2 Y2 equals to 0.22. V2 is 98.02. Y2 0.22. So Y2 is 0.00224. Okay, so that's why this one you can know already. So V2 and Y2 you know. And X2 also you know. So what would be X1 max? So X1 max you can know by using the equilibrium relationship given y equals to 0.68x. So the question here is what is y value if you want to find out X1 max. So you know that from the chart previously. Okay, let's say you have this equilibrium relationship. It's a straight line because it's just y equals mx in this case. And then if you already have this x2 and y2, then you have y1. It would be where y1 touches the equilibrium line, the one x1 max. Okay, just pretend like it's touching it. Okay, so in calculation, you can find out the relationship of y1 and x1 max using the equilibrium relationship. So y1 would be 0.68 times x1 max. So x1 max would be y1 over 0.68. So y1 is 0.022 divided by 0.68. So x1 max is equal to 0.03235. Okay, so that is your operating line at minimum flow rate. So now that you know this one you know, 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 so you need to find out the L minimum. So let's use that equation to find out L minimum. Okay, continue. So just keying in the value, 97.8 is V prime, and this is your Y1 plus L prime minimum. X2 is 0, 1 over 0. And again, V prime, and then this would be your Y2 plus L prime minimum times X1 max. We calculated 0.03235 for 1 minus 0.03235. Then we can solve for L prime minimum. Then you get L prime minimum equal to 59.24 kilomole per hour. So this solves the part A question. Okay, so for part B, you want to calculate the number of trays in the column. Okay, just take a note here. Normally for tray columns, we use the notation L0, X0, and Vn plus 1, Yn plus 1. Remember, I mentioned previously, so just to highlight to you again. Normally, this would be Vn plus 1, this is stage n, this is stage 1. Then Yn plus 1. Then this one would be 1, Y1, normally. Okay. But since from the beginning of this slide, we have used 1 and 2 as the sub. So in this case, let's use sub here is 1, here is 2. So this one would be L1, X1, here is V1, Y1, and here is V2, Y2, and here is L2, X2. Okay, either way, it's just inlet or outlet subscript. Okay, So now for part B, what would be the number of stages if you were to use L prime equals to 1.5 times L min. So we know L min already, so L prime is 1.5 times 59.24. That would give you 88.86 kilomole per hour of liquid, inert liquid. Okay, so now we use the operating line equation to solve for the actual liquid outlet concentration with the new L. Okay, let's do that. So V prime y 1 plus L x2 1 minus x2 plus to V prime y2 1 minus y2 plus L prime x1 1 minus x1. So the thing is here, this one is the same like what you have up here. Okay, this one same. Now L prime is what you will use this value. Okay, now we want to find out what would be our actual x1. So you just key in all this value. So V prime is equal to 97.8, Y1 is this, L prime is 88.86, X2 is 0, and so on and so on. And solve for X1. So then you will get X1 equal to 0.02180. Okay. So now that you get x1 is equal to 0.0280, what you do first is graphical method. You need to plot. Okay, you need to plot the equilibrium line and operating line. So you have operating line. This would be 0.68x, and then your operating line would be x2 y2 is somewhere here because x2 is 0 here. So you have y1 and x1. This is x1. Okay, here. So you plot this operating line. This is your equilibrium line. So you just step off the stages to calculate what would be the number of stages. Let's see the actual solution. So continue from previous solution. So you got x1 equals to 0.02180. By right, we should find intermediate point to ascertain if the operating line is a straight line, if we are to use a graphical method. So you can try to plot some intermediate points somewhere in the middle of the column. So let's say if you put y equals to 0.012 into this equation, you shall get x equals to this. That would give you 1 point in the operating line, and another point if you just want to confirm whether it's a straight or curve, then you put another point y equals to this into the equation and you get x equals to this. Then you plot the operating line. Okay, so this is how the plot would look like if you were to do it properly using Excel. So the blue colored line is the equilibrium line, and then the orange line would be the operating line at L prime minimum. Okay, and your actual operating line at 1.5 times L minimum is in the black color line. So you use the black color line and the equilibrium line to step off the stages. So you do stepping off the stages from here: 1, 2 stage, 3 stage, 4 stage, not until 5 stage, but if you stop at 4 stages then you won't get the outlet concentration. So maybe it's about 4.2 theoretical stages.